Communication is a bit difficult. I can't hear what I'm saying. So if you're not listening, let me know. Okay? I am César Guerreiro. I have, experience, vast experience with the prototypes. I'm in charge of prototypes in an assembly company. I spent 20 years working in product development. And then we started working with the development of prototypes of products and molds to do polyurethane. And then we worked in a transforming company of composites. There was a great experience for RTM molds and infusion molds. And then I was hired by SENAI to work with product development. So I spent like 20 years at SENAI working with development and teaching that. So in the end, you're going to see some cases. I'm going to show some cases developed. And we've been working in the innovation area of SENAI in São Bernardo do Campo. Okay?
Alô? Um minutinho, pessoal. Estão aqui reconectando a apresentação, tá bom?
Just a minute. They will reconnect the presentation.
Pessoal, a ideia é fazer uma
So the idea is giving you an explanation about molds and prototypes and their difficulties. So let us talk about the difficulties of the molding. So all of the products that will be introduced here. The case is developed by myself with some partners. There is a single presentation, and it's simply with the purpose of showing what is a product development. What is this phase?
Então, começo com definição aqui, tá? Então vamos definir moldes.
I'll begin with the definitions. Let us define mold. What is a mold? It's capable of reproducing parts. So we use the mold when we want to have repeatability. PU, thermoplastic pieces, or composite material piece. We need to reproduce. It needs to be reproducible. So we have this first cavity here, which is for the thermoplastic injection. And there is a characteristic here. Although we don't need any drawers, But it's a very complex because of the closure line. The closing line has curves. If you like playing video game, it's widely known to you. So this closing line makes this mold, complex in terms of a closure. So it becomes, a difficult mold to work with when you think about this flat line. The second image is an image that is a flat closure, and it's quite difficult to open the mold because, it's like a lid. When you think about the lid, you think about this internal thread. How can you release the lid, the cap? There are two ways of releasing. First, we call it forced extraction. We eventually use it, the plastic capability of elastic memory. But you cannot use and abuse. If you need pressure and force, it doesn't work. But if you need to have force on this closure, you need a rotation line. So this mold has a quite simple closing line, easy to do, but mandatorily we need a rotative core. Rotative core. So in every injection that you do, it's going to rotate to release the thread, and then you can open up the mold. So imagine, producing a soft drink cap. So we need to fill up with the gas. 9 to 6 caps per injection. You have a rotation system that will move 96 male parts to be able to release that cap. And the third cavity is a widely used mold for prototype development. It's a silicone module. So I need to have a reproduction of small series. Working with a silicone mold, which is a quite interesting process. We can have a small production, small scale production, and we can work with a polyurethane with no foaming agents, no expanding agents, and we produce like 100 pieces per cavity. And then the final slide there, that's a mold of vacuum forming, quite commonplace with us. Thinking about vacuum forming molds, we can think of in this case packaging, for example, and in this case here, packaging to export figs. Oh, fig fruits. So we made this development we had this fig producer. He was interested in exporting the fruit, but that they would get crushed. So we developed this mold here that is capable of, storing the fruit. It doesn't crush. You set up one on top of the other, and you don't have the crushing of the fruit. Let's define prototypes. They're prototypes to many things. All prototypes have this objective. That is a piece that has this objective to do the proof of the design. So very often you do this project and you want to get visual approval. So sometimes you do this project, you need to validate raw materials. So there are many situations, right, that in which you need to validate the product. And what do? You do a prototype. And today with the new technologies, there are possibilities of validating all of that in a virtual fashion. Not always is this possible. We'll see details later. This first image here is an image that we had when we were working with the technician. So we did this development with this car. And in developing this vehicle, eventually many stages were covered. The virtual assessment, the visual assessment. We could produce, milled parts, 3D printed parts as well. And this image here, this picture, shows this virtual picture of the whole set, of the chassis. Let us talk about this a bit more. The second image is a piece that is milled. So this piece here that is milled is a way of obtaining prototypes. When you say we're going to get the prototypes, we're going to use 3D printing, it's wonderful, it's a fantastic tool, and there are other processes. And CNC milling in a polyurethane board is just one of the possibilities. They will ensure, good quality, perfect dimensions, and so on and so forth. But it requires some techniques. You can see this area outside the wheel. There is the geometric shape that helps in the milling. We have 4 axes of milling, so we can mill this part quite easily. The third picture is a demo only. It's a 3D piece. It's an old technology called Object that enables us to build parts, layers of 16 micro. This really enables us to build the wonders that only 3D printing allows us to do. Okay, this is how they operate. And the final image is results. Results of modeling in a styrofoam, the manual process. How to ensure symmetric results, even results. And then we do the visual approval, the visual check. But then they carry out a study. They do this development. 1 to 10 scale, 2 people, 2 meters, that's the requirement. Okay, so I'm going to show you the mold, some processes. That's a cavity. That's the epox resin. And why do I do that? And then sometimes you have to inject. That would be what I classify as a structural prototype. So it must be injected according to the project material and according to the processes that are foreseen. So one of the possibilities of producing this cavity is using the epoxy resin. And then the second slide that you see here, it's a virtual model being prepared by 3D printing. In order to get this first cavity, we need a model, right? Or if I take, steel and you mill a cavity, when you work with the epoxy resin, we have the need of having this physical model and apply the resin on this physical model. It's a cap. It's like a lid for a cup. We had modeled this before. We had the model virtually. We did the modeling. And in this case, they are creating the layers to do the 3D printing here. So they did the 3D printing. They found the closure line. We applied the epoxy resin in the matrix. So they organized this in a back mold and they introduced in the injection machine. How many parts can you produce, you might ask? Well, that will depend. And it depends on the resin that is being injected. It depends on the geometric shape of the piece. But we were able to produce more than 150 pieces in such a cavity. And a mold with metal done by 3D printing by means of laser sintering process. It's a quite interesting process when we need to have a large amount of prototype parts. So one of the advantages of this mold and working with this technology, that's the tooling of the future. Because when you work in injection of thermoplastics, well, how am I going to have a high production of thermoplastic? Well, if I don't have a cooling system. Well, what do we do with the mold? You take the steel block, you mill it, you drill it. So in this 3D printing process, you may have your cavity, and then the cooling channel can go along the cavity. That's what I can do. What's the advantage? I may have smaller cycles because my cooling system will be more efficient, okay? And then the last image. It's also a mold cavity by 3D printing with a polymeric material. This leads to limitation in production because the polymeric material in the cavity will result in lower durability. We are aiming at having a small number of pieces. So if you do polymeric material cavity by 3D printing and by epoxy resin as well, you're going to have limitation of the processes. And in this case, limitations, it's not only in terms of the number of parts produced. It's difficult to do the dispersion of heat because in polymeric materials, they hold the temperature, and it's difficult. Well, and it's nothing good when you are producing and you want to have faster and larger production. If you want more production, mandatorily, you need to promote thermal exchange, and some materials will not enable that. And then thinking about classification. And we talk about prototype classification. Why prototype classification? Why do I classify? Because I may have a prototype. Well, depending on the class, I have a differentiated mold. We're going to invest more or less on the mold, depending on the construction stage. And here, let me show you some processes. The parts that you see here on the left, well, this was done by 3D printing. And here I can do an assembly. I can see whether the project works or not. So that's what I can do. So you have the center here, and that was the prototype that we built, one-to-one scale here. Look at this. So this vehicle was a project. In the middle, as you can see there, a Cuban project for one person. It's an electrical vehicle, 2 engines in the back wheel. In the back axle, there was a whole mechanics, electronics operating so well, but they had to use the entire structure. So the demand was producing this in 2 months. doing the modeling, the mold, and the part production. So I would say that it's technical work. So we had to manage the entire project in detail. Every single day we were assessing how much we had advanced to reach the results. So modeling was done in styrofoam. We'll see the comparison later. And the 3D printing, well, can serve any economic segment. Footwear, they also work with 3D printing. Well, the companies that supply polyurethane for footwear, perhaps you have to share and use the PU tools, the 3D printing tools, so that we can produce the footwear, the shoes in this case. Okay. How about the classifications in 3D printing? We classify in virtual prototypes, visual prototypes, dimensional and structural prototypes. What are they? Let's see what they are. What is that? Well, in beginning with the development phase, the creation phase, sometimes there is a demand of producing a certain piece or a set of pieces. So you model the pieces individually. So let's compare if we assemble or do not assemble, if there's going to be an interference or not. So this project was developed by students from the Technical University with Senai, and they produced one car, one vehicle for 2 people here with 7 parts. Look at this. So here we have some of the parts: the tire, the wheel, the semi-axle, the chassis. So what is a virtual project? We work on the CAD system. We do the modeling in the CAD system. It could be ANX, SolidWorks, and then we do a CAE assessment, so we can obtain, the volume, the mass. We can do the assembly as well, and we can do an assessment, a virtual assessment, with no major manual investments. We don't need to invest in the mold, in the materials. So you test, you see if it is, compliant with the requirements, and then you move on to the next phase. So that's the image that you see here of the wheel. So that's something that facilitates the milling process, as I said before. You see the final chassis, and then you see, the area to hold. It's an interference, but it's an interference that has been designed for that purpose. It's the support on the sides that you see there. That's the visual prototypes. What are those? Well, these are phases of the project. The cars can be tested by visual prototyping. This first model shows a vehicle done in clay. There's much manual work. Although technology, and we have been advancing, this process has been facilitated. So you do one side of the car, you do one side of the vehicle, you get the visual approval. And of course, it's not just about the visual approval. You have to respect the distance between the wheels, the axle itself. The ergonomics of those who are going to drive the vehicle. And then you do the modeling. Okay? And then we do the scanning of the surface. We do the mirroring of the surface. We do a CNC milling process that is appropriate, and then we do everything else that is required. And then you have a symmetric vehicle. So this is how we go about attaining symmetric results. It doesn't mean that it's ready. You can mill on the other side. It is asymmetric. And then you find the person to approve the project. They're going to look at the vehicle and say, well, let us change it here, change it there. Sometimes that is rework that happens throughout the process. And then we finally get our model that was produced in 60 days. Look at this. And we replaced the clay by styrofoam for the prototyping. So the modeling was done in styrofoam. Styrofoam has a higher density. It's not easily found. And then we modeled the vehicle. In the case of this vehicle, we couldn't change very much after being modeled. There was no time to, change. But it could be used with a styrofoam. But the difficulty in, going up and down, doing this visual approval, it's much more difficult than in a clay. And then in styrofoam, it's more difficult to change. Going back and adding material to styrofoam, it's not easy. You have to add a board, remove a board. If there is glue, it's stiffer. There are issues in modeling if it gets stiffer. So you need to work on this when you have a more defined geometry. Dimensional prototype. What is it? Well, in this case, we can get those from 3D printing. And then we can measure this piece. Okay, we set it up, it worked. Even if the material used is not the material that you had thought about for the final project. This part is used in the engine of the Mercedes truck and forged steel. And this was done in the sterile process. And we can add this to a truck. You can assemble this on a truck. You can stretch the belt. We can actually make an assessment with this part. We can assess whether this part will interfere with the counterpiece or not. When you stretch the belt, if you're going to, touch another part, third, fourth piece, and then you decide whether you continue with the project or not. So the visual prototypes give us the possibility of analyzing the counterpiece. The other image, it's the silicone mold. What does it have to do with the dimensional phase? Sometimes you need to get a pre-series. The pre-series part should not be a final part. You have to simply analyze. Well, you have to develop a device. So we need to make some assessments. But it doesn't require structural strength. Then you can supply the pre-series and check whether everything is okay. The final image, also allows you to reproduce small pieces. But then you see the rigid resin, epoxy resin, and another part that is made of silicone. So why do they work like this? When you work with the silicone mold with larger cavities, what happens? So you go there, you go on a bench, you do the matrix, you do the mail, you get the specimen, and then you need to reproduce the part. So you take this mold that is flexible, you put it on a wood bench that is warped, and then it's going to copy the shape of the wood, and then the piece is going to be deformed, right? To prevent that from happening, we can do a rigid matrix and a mail that is flexible in silicone, okay? That's a solution for large pieces, bigger pieces. That's a cardiac tracer. People from Dante Pazzanesi, the Heart Institute, they used this part here. Look how interesting this is. What is a structural prototype? Well, in their project, they defined they're going to use polyamide, 30% fiber polyamide in an injection process. What's the assessment? Whether it's going to withstand the stresses or not. What should be done? There's no way around it, no other possibility. This part has to be done in injection with fiberglass polyamide. There's no way around it. And then we have the cavity that is done by laser sintering. Do you have any better idea about the structural prototype? We can replace this oil rod for measuring oil in the vehicles, the thing that measures the oils, the oil stick. So you measure the level of the oil to see if it's okay or not. So we can replace the metal by fiberglass polyamide, a polymeric material in this case. So what are the stresses on the rod? The chemical attack of hot oil. It's the chemical attack and the temperature, the high temperatures. So if we are to do a prototype of this rod, it has to be injected. And the material should withstand temperatures. But mandatorily, you have to do an injection mold for that purpose. You have to do that. And here, first images. Because they had to produce this lid for the cup, and then they modeled the cup, 3D printing, they got the physical part, and then after the physical part, they produced the cavity in epoxy resin. And then there was this amount of pieces that was produced. You cannot use epoxy resin too much, right? Well, this is what we do to get the injected piece. In this case, this part was done in TPU, thermoplastic. And the last one was this work to replace the pulley. It's a washing machine pulley. So we would replace the pulley in aluminum, made of aluminum, with polyamide 30% fiber. This was a dissertation article. The student could not visualize. He was a tool developer. He worked with aluminum, and he was amazed by the amount of rework. So he developed this project to produce this polyamide piece. When we think about replacing a metal by a polymeric material, you have to think about the differences in property. There are huge differences in property. One is more flexible, the other one is more rigid. So what's the point? You have to think about changing the geometry to be more robust, bigger, with more notches. So the pieces will define the conditions. So we increase the number of, rods in the hub and spoke. So there was a drawer because we wanted this internal tear. In the aluminum, it was milled, but we wanted the piece to be ready for the belt, to work with the belt. So 4 drawers were produced to be able to inject this part. Look at this. Controversial issue now. We talk about bridge production. And then it's quite controversial. I mean, what is a bridge production? Well, you do the prototype was approved, that's cool. But I need 1,500 pieces per day. 1,500 pieces per day. And then production engineering is not appropriate. the product is new. So how can we get this piece, this batch of pieces? That would be the bridge production. That's between the prototype and the final production, okay? There's a whole segment that works with 3D printing, and they say that it's possible to do that by using 3D printing. And we can only get this by using mold and prototyping. Well, based on my experience, what will define one thing or the other, that will depend on the piece geometry, the size of the piece. If it's a small piece, perhaps, 3D printing will meet a demand. If it's a bigger piece, that's more difficult. Only a prototype and molding will solve the issue. Very well. That was my presentation, and I hope you have learned. I hope you have gained experience. Well, if you need more explanation, or if you would like to see the parts, we'll have something at Sinai. Thank you very much. Thank you very much for listening. Wish you all a nice afternoon.
Alguém tem alguma pergunta?
Any questions?
Tá tudo certinho?
Is everything all right?
Qualquer coisa é só passar no stand. Então,
let me know. Visit our booth.
Muito obrigado.
Thank you very much. Very nice presentation.